Okay, let's go over the homework for this week. Hope you've had time to get it done. Should be something that you already know how to do, but we'll go through it just to make sure in case you were a little rusty on it. Problem number 1 on page 199 says to fill in this factor tree with the information we have. We have the prime factors, but to fill in the blocks, just starting from the bottom, you know that 5 and 11, that has to be a 55 here. And this block would be 3 times 55, so that's 165. And then this block would be 2 times 165, which is 330. Okay, and then part B is how could you get, even if you didn't have any of the blocks filled in, how could you get the number without these two? And this is the prime factorization, 2 times 3 times 5 times 11. So that should give us our number, 330. 6 times 5 is 30, and then 30 times 11 is 330. So the prime factorization itself should give us this top number without even going through those. Okay. Number 2, it asks us to use a factor tree to find the prime factorization of 504. All right, I'm going to erase some of this so I'll have a little bit of room. Okay, now we can start off, of course, with the numbers, any two numbers you can think of that are factors. I had these all written out, but that's okay. If we can think of two factors, we can see that it could be 2 times 252. I can see that 4, since the last two digits are divisible by 4, I think that's what I'm going to use, just to be different. 4 times 126. Now, neither of these are prime numbers, so I'm going to keep going. 4 is 2 times 2. Those are prime, so I'll circle them. For 126, I'll use 2 times 63. All right, there's a prime. And then 63 is 7 times 9. There's a prime. And 9 is 3 times 3. I've got all primes now. So my prime factorization for 2a, I have 2 as a factor 3 times. So 2 cubed times, I've got 3 twice, 3 squared times 7. And that should equal 504. Okay, number 2. B, we're going to do 2475. Most of us would probably think of the number 5 because the last digit is a 5. So let's do 5 times 495. This one is prime. We can go again with a 5. Let's see, that's 5 times 99. And then 99 is 11 times 9. I'm circling primes. Okay, so that one would be 3 squared times 5 squared times 11. 3 squared times 5 squared times 11. Okay, our last one on number 2 is 11,250. Again, we can start this many ways. We could start 2 times something, 5 times something, 50 times something. I think I'll start at 10 times 1125. Now 10 can be broken down to 2 times 5, both of which are prime. And for 1125, I think I'll break those down into 25s. I'll see, I think quarters here. And that's 25, ooh, that's not prime though. 25 times 45, and then break those down. And 5 and 9, of course 9 can be broken down again. So what we have is 2, see that 2 there, times 3 squared times 5 to the 1, 2, 3, 4th. And if we multiply all that together, that should give us 11,250. And then question 4, what is the highest number, let's see, what is the greatest prime that must be considered to test whether 769 is prime? All right, well, would consider the square root of 769. And if you just play with. If you don't have a calculator, you know it's going to end in 9, so it would have to be a 3 times 3. So it was not 3 times 3, it's not 13 times 13. Let's try 23 times 23. 3 times 3 is 9, 3 times 2 is 6, 2 times 3 is 6, 2 times 2 is 4. Did I do that right? And let's see. Am I not doing something right? 6 and 6 is 2. That's 529. Not enough, is it? So let's try 33. That's 9999. That's going to be too much. I could have sworn that it was, it's, let's see. So it's between 23 and 33. Maybe this is not a whole number. Let's see what, we know that 23 is not enough, 33 is too much. So let's try something in between. I happen to know that 25 squared is 625. That's not enough either. Let's try 27. How about that one? Because 7 times 7, that's a 9. 49. Let's try this one. There we go. No, but that's close. That is as close as I believe that we might get. Let's try 28 and see if we have too much. 4 and that's 22. That's 784. This is 28's too much. 27's not enough. So it's 27 point something. So our largest whole number would have to be 27. I could have sworn your book said the answer was 23, but you know I can't see. Let me look very closely. Yeah. It says 23, but that is, oh, I see. Here, 27 is the greatest whole number, but the question is, what's the greatest prime number? Well, if we go backwards, 26 is not prime, 25 is not prime, 24 is not prime, 23 would be the greatest prime. This is the greatest number we would have to check, but if we're looking for a prime number, the greatest prime number is 23. Okay. That explains it. You got to read the question carefully, which I almost did not. All right, let's move on to the next one. It was a word problem, and I believe it was number 15 on this same page. Again, let's do a little bit of erasing. All right, and in this one, we're talking, I'm going to pick the book up so I can read it. Number 15, Miss Cotton wants to put her classroom in a rectangular array. For each of the following numbers of desks, find all possible numbers of rows if each row has the same number of desks. Well, for 30, she could just have one row and put all 30 in them. 1 by 30. Or she could have 2 rows and put 15 in each. She could have 3 rows and put 10 in each. Now, can she have 4 rows? No. Not and have the same number in each row, because 4 times no whole number will give you 30. But 5 times 6 will. So she could have 5 rows. And of course, we could say 6 rows, 10 rows, 15 rows, and 30 rows. Any of these numbers, any of these factors could be the number of rows. If she has 15 rows, for example, she will have 2 in each row. All right, B, what if she has 28? We're going to do the same thing. We're going to figure out the pairs of factors. 1 times 28, 2 times 14, 4 times 7. And that's all. So the rows, you could have one big row with 28, 2 rows of 14, 4 rows of 7, 7 rows of 4, 14 rows of 2, or 28 rows of 1. All right, C. If you have 23 in your class, you can either have one row of 23 or 23 rows of 1. So these are your only choices, 1 row or 23 rows. That's a prime number. All right, and D, 120. Might use up a lot of room here. We can have 1 row of 120, 2 rows of 60, 3 rows of 40, 4 rows of 30, 5 rows of 24, 6 rows of 20, not 7 rows. We could do, 8 rows of 15. Notice how these numbers going down the left are increasing, the ones on the right are decreasing, and these two numbers are approaching the same value. We can go one more, 10 rows of 12. And those are very close. I'm suspecting that's the end of it. The square root of 120 is 10, almost 11, but not quite. So we've tried enough. But I can have 1 row, 2 rows, 3 rows, 4 rows, 5 rows, 6 rows, 8 rows, 10 rows, 12 rows, 15 rows, 20 rows, 24 rows, 30 rows, 40 rows, 60 rows, or 120 rows. All right. Good question there. Sounds like a good quiz question for me to put up for you. Okay, let's see. Number 16 was our next one. Do a little bit of erasing again. Same page, page 199. Okay, again, I need to pick the paper up, the book up to read. Bria and Emma are on the same swim team for the summer. The coach placed each team member on a different training schedule. As a result, Bria swims laps every other day and Emma swims laps every 3 days. The schedule begins on the first day with both girls swimming laps. How many times will Bria and Emma swim laps on the same day during the first 10 weeks of summer? Well, we know that the girls, 10 weeks of summer, 10 times 7 days, that's 70 days. So the days are days 1 through 70. Now, they're going to swim. Bria's going, let's look at Bria's. Bria's going to swim on day 1, 3, every other day, and so on. So she's swimming on all the odd number days. And the other girl, Emma, she's going to swim on day 1, so they've got one alike. And then she's going to swim every 3rd day, so that's 4, 7. Now, we're not going to continue to do this, but what's happening is it's every 6 days. That, let's see if that holds up if the next one comes out 13. All right, this is Bria's. Let's extend Bria's. Now, 3 days later, Emma comes, 3 days later. So, yes, do you see how it's happening every 6 days? They started, that's 1 plus every 6. Now, so all we have to do is figure out how many times this is going to happen. Well, 6 times 11 would give us 66, so that'll be 11 times in 66 days, plus this first one when they started. So plus one more day here. And let's see, I'm hoping, let's see, that's 12. I'm going to have to pick this book up and read it again. Yes. So it would be 12 times because it's every 6 days, but you have to consider they both started on the first one and have one day together there. Okay, and the last one of these, number 17. Let's check that one. A woman with a basket of eggs finds that if she removes the eggs from the basket, 3 or 4 at a time, there's always 1 egg left. And if she removes them 7 at a time, there are no eggs left. So I know if she removes them 7 at a time and there's none left, it's a multiple of 7. So that means that it's either, there's 14 of these, 7, 14, 21, 28, 35, 42, 49, 56, 63, 70, 77, 84, 91, and 98. Alright, so it's one of those 14 numbers. But it also says that when she lists them out by fives, there's one left. So it's a multiple of 5 plus 1. This is not a multiple of 5 plus 1, because that's 5 plus 2. This is not a multiple of 5 plus 1. That's a multiple of 5 plus 4. Now this one is, so this one's still a possibility. 21 is still a possibility. Multiple of 5 plus 1, no. That is a multiple of 5, so it's not plus 1. That's not. 49, a multiple of 5 would be 45, nope. A multiple of 5 plus 1, that one is possible, because the multiple of 5 is 55. This one, nope. That is a multiple of 5, so nope. This is a multiple of 5 plus 2. That's a multiple of 5 plus 4. This is a multiple of 5 plus 1. And that's multiple, nope, that's plus 3. So we're down to 3 numbers left. So our next clue was if she picks them out by 3s, there's one left. So it's a multiple of 3 plus 1. Well, this is a multiple of 3. There would not be a plus 1. All right. This is 11. If you add up the 2 digits, 5 plus 6 is 11. For it to be divisible by 3, it would have to add up to 9. So that's 2 too many, not 1 too many. 54 would work. And that's not leaving 1. So I hope this one works. I hope 91 is the number. Well, we know that 90 is a multiple of 3. Because it's 3 times 30 plus 1. So the answer is 91. That's a multiple of 5 plus 1. Because 90 is a multiple of 5. All right, so we're ready to go to the next page, which is page 212. All right, everybody turn to page 212 while I clear my board one more time. All right, and I asked you to do number 3, and I said by any method, and I'm going to do my favorite method, which is the slide method. And I've already done them somewhere trying to save time, and I might spend more time looking for it than I do anything else. But let's see. Here we go. We're going to find the GCD and LCM for 132 and 504. All right, we're going to put both numbers down and put the line. All right, now I can think of any number that will divide both of those. And I see they're both even, so I'm going to use a 2. And divide it into both of these. 2 goes into 32 66 times. And into 504 252 times. All right, now can I stop, or do I see another number that will divide both 66 and 252? Yeah, I'm going to try another 2. 2 goes into 66 33, and into 252 126. Okay. Do I stop here, or I know they're both not going to be divisible by an even number. 2 or no even numbers are going to work, but let me try. 5's not going to work. Let's try 3. I know this is, and these add up to 1 plus 2 plus 6 is 9. 3 is divisible by 9, so yes. 3 goes into 33 11 times. 3 goes into 126 42 times. Now, unless 42 is divisible by 11, because that's the only thing that will divide 11, we're through. So, our greatest common divisor is the product of all these divisors in this column. 2 times 2 times 3, which is 12. And our least common multiple is the L shape here, the column and the bottom row. 2 squared times 3 times 11 times 42, which is 5,544. That's so much easier than any method I know of. That's the one I like, but you can choose. All right, but this is the way I'm going to be showing you because it takes care of both. All right, let's do the next one. If you do the listing method or the, whatever your book calls it, method, intersection of sets, you have to make two different lists. You could do the factor trees though, and just know what to do and you'd be okay. Wouldn't be as much trouble. For 65 and 1690, I see one ends in a 5 and one ends in a 0. So I'm going to try the number 5. And this will divide 13 times, and this one 338. Now I'm through unless 13 divides 338. Well, it does. So it divides in 13 once and 338 26 times, and nothing divides these. So our greatest common divisor is the left-hand column. 5 times 13 is 65, and our least common multiple is that same column, 5 times 13 times 1 times 26. So basically 65 times 26, which is 1690. All right, and C. Let's see. For C, we had 3 numbers. Okay, 96, 900, and 630. Let's start off with 10. No, I can't because that's 96. Let's start off with 3. And that would be 32, 300, and 210. That's just doing the division. Now those are all even. I'm going to use a 2. And that gives us 16, 150, and 105. That is the end of it. So our greatest common divisor is 3 times 2, which is 6. Our least common multiple is 3 times 2 times 16 times 150 times 105, which is 50,400. Now, I haven't mentioned this yet, but least common multiple is the same thing as the least common denominator. So if you were adding and subtracting fractions with these denominators, you'd find in the one that's common, that would be it, 50,400. Okay. We have one more of these. All right, D is 108. And 360. I think I'll do it a different method. Instead of the slide method this time, I think I'll do a factor tree. Let's see, 2 times 54, 2 times 27, 3 times 9, 3 times 3. So that's 2 squared times 3 cubed over here. And for this one, I'm going to use 10 times 36, 2 times 5. Let's see, 2 times 18, 3 times 6, and 2 times 3. So for the greatest common divisor, I want to find what they have in common. Oh, I better write this.